Hi, everybody. This is part two of correlation, and this relates to hypothesis testing. I'm starting halfway down the correlation slide deck with the information so we can discuss how hypothesis testing works. And when I think about hypothesis testing, it's a formal process for organizing research information and reporting it with the least amount of bias possible. Some people might have heard of the so-called scientific method that's often taught in schools, secondary schools. Um, I don't know many scientists who follow the scientific method, but the scientific method is a form of problem solving, and it's a hypothesis testing method, basically stating a hypothesis and trying to demonstrate its accuracy or inaccuracy based on available data. There's lots of forms of problem solving. There's trial and error, root cause analysis, lateral thinking. So there's lots of ways to approach problem solving. This is a specific methodology that is built into the tradition of doing quantitative analysis. Okay, so there's some notations I want everyone to be familiar with, and these notations are the HO and the HA. So H subscript O is the null hypothesis, and H subscript A is the alternative hypothesis. So to reduce bias, what we say is we have a null hypothesis, and the null hypothesis is always the same. It assumes there's no difference between whatever is being tested. So in a correlation, we assume there is no statistical relationship between variable X and variable Y. And then there is the alternative hypothesis, which you state in advance, that there will be a statistically significant relationship between variable X and variable Y. There are two versions of the alternative hypothesis. There's a directional hypothesis, meaning you say which you think is going to be better. So for the alternative hypothesis in a correlation and a directional one, you would say there is a statistically significant positive correlation. You're stating in advance what you think the relationship is going to be. And then there is a non-directional hypothesis. There is where you don't care, you don't say anything. I'm personally a non-directional hypothesis person. I don't believe in introducing any bias at any level. So my choice is always non-directional when making a hypothesis. Um, there are other scientists that feel differently. They think research might suggest that directional hypotheses in a specific situation might be appropriate to state. Totally up to you as the researcher, as you build your philosophy of quantitative analysis. My bias personally is I go non-directional because I don't want to influence any of the decision-making process. So when we think about statistically significant, that goes back to our definition of P, or the p-value. And in educational research, typically we set a p-value of 0.05, the alpha it's sometimes referred to. In advance, we say we're going to look for statistically different information when the p-value is less than 0.05, less than or equal to 0.05, and something is statistically similar if p is greater than 0.05. And this is a standard relationship. It's one you really want to lock in with and understand well. Less than 0.05, statistically significant. Something is whatever. And greater than 0.05, statistically similar. So we're going to look at the directional versus the non-directional, and those are called the tails tests. So if you have a two-tailed test or a one-tailed test, that gives you an indication. So if you're going directionally, you're saying that like this is where the difference is going to be. Either this is less. There's a negative relationship, for example. The benefits to doing a directional test and why some people choose to do them is because you get all of the error in one place. A two-tailed test, you have to split the 5%, the p equals 0.05, between this possible choice or this possible choice. So when the data is in the middle, this kind of makes sense, right? When the data is in the middle, it's similar. When the data falls on the far end, it is statistically different. And that's where the p-value is less than 0.05. So when it comes out here, it's less. Okay, so let's let's give an example of a hypothesis in the null and alternative form, both the non-directional and the directional. Now, what I think is important to note here is there is language. You don't need to create this language over again. It's like literally fill in the blank. You use the verbiage exactly how it's written, and you fill in your pieces of information. So here's the null because we say there's going to be no difference. So there will be no statistically significant correlation, p greater than 0.05, because that's the p-value of no statistical difference between so the instrument is the MSLQ, or the Motivational Strategies for Learning questionnaire. It's an instrument that's used to look at motivation. There are a number of subscales on it, including intrinsic motivation and extrinsic motivation. I will show you exactly what these look like data-wise and how we analyze them for the correlation in video number 3. So there will be no statistically significant correlation, p equals less than 0.05, between factor one, X and Y, intrinsic motivation, extrinsic motivation, as measured by instrument that's being measured. So you can see the language is very straightforward. The only place you're going to be changing is the variables and then what you're using to measure those variables. Now let's look at the alternative. There will be a statistically significant correlation, p is equal to or less than 0.05 between intrinsic motivation and extrinsic motivation as measured by the MSLQ. That's the two-tailed version because you're saying there isn't, there is. We're not saying where it is. Now let's look at the directional version of the same thing. There will be a statistically significant positive, there's the direction, correlation between intrinsic motivation and extrinsic motivation as measured by the MSLQ. That's the one directional. This word could also be negative correlation. So either version would be fine in this situation, depending on why you're choosing a directional hypothesis. You must have some background information that would support saying this. You wouldn't just randomly say it. There would probably be some literature support to suggest why this would be the case. And those are the hypotheses. Now, when we look at the results of the correlation, you're going to get this table that forms out. And the Pearson correlation is the calculation, and then the significance will be measured. I set mine up for a two-tailed test, and I did set a significance at the 0.01 level. For this case, that was just the demonstration I have. So there are 127 in the sample, and what we see is this is called an intercorrelation matrix. And what we see in the intercorrelation matrix is intrinsic, intrinsic. There's obviously a perfect correlation because it's the same data. So it reports as 1. And then intrinsic to extrinsic, a 0.438 correlation. And that is then we report whether it's significant or not. And in this case, yes, it is significant because it's less than 0.05, or in this case, the way this test was originally generated was less than 0.01, even more robust than that. You see intrinsic to intrinsic, intrinsic to extrinsic, then it formats the other direction, intrinsic to intrinsic, and extrinsic to extrinsic. There must have been some extra data points here, so that's why there's a couple more here if you're trying to interpret that. This data here, because it's the same as this data here, is going to match itself. You'll see this if you're doing multiple variables at once, you get this matrix and you'll find that there's one to the other. Let's look at another set of data from the MSLQ. This is the self-efficacy and the test anxiety relationship. So in this one, I did some descriptive statistics in advance. We can see the mean, 0.5, 5.1, median, so on, standard deviation. We just can look at these. Got some standard, some skew and kurtosis. They look nice values based on what we've talked about before. Remember, between -1 and +1. And then here's the correlation. I'm sorry about the extra little logo here, but it doesn't really matter because, again, we got the diagonal situation. So in correlations, test anxiety related to self-efficacy, we see the correlation is a negative 0.285. So negative means a negative correlation. And then the significance, it's there, 0.001. And the 2.285 is right beneath it. So let's look at those results again. There will be no statistically significant correlation. There will be a statistically significant correlation. We reject the null. We accept the alternative that there is a statistically significant little to no correlation between self-efficacy and test anxiety. If you remember, we have the rules of thumb for interpreting the size of the correlation coefficient. And so if you remember from here, the correlation is negative 0.285. And so we find point negative 285 is down here, which interprets as little, if any, correlation. So when we go back and we put the language in, there is statistically significant little to no correlation between self-efficacy and test anxiety as measured by the MSLQ. Here's another one. This is intrinsic goal orientation versus task value. And we see the values here, again, the same on the diagonal situation. They're going to be the same. This has got a big one here, 0.739, statistically significant. And we're just interpreting the information. We look at the raw descriptive data here. We actually look at this in a graphical form. We can see that positive relationship taking place. If we were to imagine the line of best fit in there, looks like it would be right there. So let's take a look at the writing on this. Again, we're following a pattern. That's what's critical in this information. Follow the pattern. There will be no statistically significant correlation, p less greater than 0.05, between intrinsic motivation and task value as measured by the MSLQ. There will be a statistically significant greater than. We reject the null and we accept the alternative. And let's do the write-up on this one. I added one thing in this one. If you want to add a little more detail, this is an optional part, but sometimes it's worthwhile. It's definitely worthwhile when you do some of the other tests. There is a statistically significant, p is less than 0.05, high positive correlation, get that from my rules of thumb, r equals 0.74, between intrinsic motivation, and then I put the average of what intrinsic motivation was. So 4.53 and task value 4.99 as measured by the MSLQ. And you would get all that information from the descriptive statistics and the correlation table. This is called a correlation matrix. You can actually run multiple variables at the same time. I've done two. If you do that, again, you're going to always have the matchups, intrinsic, intrinsic, task and task, extrinsic, extrinsic. You see how they match up. And then the two sides on the triangle mirror each other. So everything over here is the same thing that's over here. So what I typically do is if I'm making a correlation, intercorrelation matrix, which is what this is called, I just put the one side of it on because I think it's just a little distracting sometimes to have two sides to the correlation matrix. Here's task anxiety versus task value. Super low correlation, 0.021, like this close to zero. And if you look at the significance on this one, here's the p-value, 0.81, not statistically significant. So that would be an example of where you would accept the null and reject the alternative. And the null is always, there's no difference. There's nothing there. When we interpret R values in terms of the variance, it's not only a measure of the relationship between the variables, there's a proportion of individual differences in one variable that can be associated with the variance of another. Because remember, you're not doing a point to a point. You're doing a set of data and another set of data. So that's how we have to think about it. And obviously, correlation does not mean causation. Other factors could be contributing to the individual differences. If you go to the correlation unit in Blackboard, you will see there is a correlation template. And if you open that, it'll make a copy for you so you can make as many copies as you need to do. And this is really a tool that I've designed to guide you through the hypothesis testing process. So state the research question. We're not going to do that yet because we haven't gotten there yet. But we're going to state the hypothesis, and we do the null first. And then we do the alternative second. We set the criteria for rejecting the null. That's what's 0.05. No secret there. You compute the test statistic, which is R. You do that in SPSS. And then you interpret the results. Okay, and this tells you why you're doing it. and the purpose of each. So use this template. You can actually use it right for the assignments that you're going to do. I have a number of different ones for the different statistical tests that we do, but this one is the one that's specifically designed for correlation.